you feel you can't reach it.
Ok, boa tarde e bem-vindos a todos. Este evento será feito em inglês, mas queria primeiro dar as boas-vindas a todos em português. Good afternoon and welcome. As a member of both the Ordem dos Engenheiros and the Institution of Civil Engineers, I am incredibly honoured and privileged to be hosting this event on behalf of both the organisations. As many people know, I am technically British, but this is my home city, and I started studying physics across the road before I embarked on a journey of engineering. First of all, I'd like to thank each and everyone who is attending in person and online. I think we counted approximately 50 people in person and also 50 people online in the UK and also in Portugal. So thank you very much. Would like to extend thanks to the Bastonário of the Ordem dos Engenheiros, Engenheiro Fernando de Almeida Santos, for the invitation to our president to come to Portugal. I'd also like to extend thanks to the President of the northern region of the Ordem dos Engenheiros, Engenheiro Bento Wise. Unfortunately, they were not able, due to travel commitments, to be here. But I'd also like to extend thanks to the President of the National College of Civil Engineering of the Ordem dos Engenheiros, Engenheiro Humberto Barum. Thank you to all the speakers. I apologize, we had some technical issues with the website, so we were unable to upload everyone's biography and photos. However, we tried our best and we've printed out some hard copies for those here. And also we circulated PDFs to give the broad range of experience that we've tried to bring here in collaboration with the Ordem and the ICE, reflecting the experience across Europe. I'm just going to press this. I don't know what's happened to this slide. Usual technical glitches. Okay, welcome introductions. I've done those. So we'll have two addresses from each institution. This is very much trying to be in collaboration between both institutions. And then we'll have a series of project presentations, as I said, covering a variety in depth and breadth across Europe. What have I done here? Some closing remarks really to wrap up at the end, and to us a very important part is the networking session afterwards, where we invite everyone downstairs to socialize and get to know each other. As context of why a lot of people from the Institution of Civil Engineers are here, today we had our European planning meeting in Porto. We are an organization of 97,000 members across, Tom, can you correct me, 168 countries. And we have a group of representatives across the European countries who are listed here, and 16 of which have traveled out. And today we had a full day meeting, internal meeting, but we wanted to combine this with an event with the Ordem dos Engenheiros. So please, we've all got name tags, so please introduce yourselves. We are very welcome to and encourage talking to others. So I'm going to bring up Julia. Pardon? Oh, no, sorry. This is going well. That was the icebreaker. So I will Thank you.
So, good afternoon, boa tarde a todos. Dear President of the Institution of Civil Engineers, David Porter, dear representatives of the Institution of Civil Engineers, allow me please to address a special greeting to Daniel for his commitment, helping in this relationship between our institutions. Dear members of Ordem dos Engenheiros, dear colleagues, ladies and gentlemen, it is a great pleasure to me to be here with you today representing the Order of Engineers in the name of our Bastonário, the President of the Order, Fernando Almeida Santos, send to you all his regards. And it is for me a great pleasure to participate, particularly today, in this bilateral meeting between our institutions. Allow me, please, to express our appreciation to ICE for the invitation to associate the Order of Engineers to the organization of this very important and relevant meeting. The Order of Engineers really values the spirit of proximity that characterizes the relationship between our institutions. We are speaking of two institutions with a consolidated history of public responsibility, with technical and ethical standards at the highest level. And our institutions share a mission that I would like to highlight. Our mission, our common mission, is to value engineering, to qualify professional practice, and to place the knowledge of engineers at the service of our society. This meeting is therefore, for us, more than a technical knowledge sharing session. It is also a sign of trust, cooperation, and shared willingness of build bridges, or to build bridges between professionals in Portugal, United Kingdom, and Europe. And we all, as civil engineers, understand very well the meaning of bridges. For us, they are not only the nice structures that we design and build. You'll see very nice examples today. For us, bridges are also to be established among institutions, among professionals, those human bridges that bring together people, knowledge, companies, countries, and regions. Civil engineering, at least in Portugal, but I'm sure also in UK will listen to you, is currently facing a particular demanding moment. We are confronted with many major challenges. The maintenance and renewal of the existing buildings and infrastructures, the adaptation of the society and as well as our infrastructures to the climate change demands, the energy transition, the decarbonization of construction, digitalization, structural safety, housing, mobility, water, and the need to ensure a more resilient, sustainable, and inclusive built environment. These challenges are global, but they are felt very directly in our countries as well as in our communities. At global level, investment needs in housing as well as in infrastructures continue to grow. The Global Infrastructure Hub has estimated that these needs could reach around 80,000 billion by 2014. At the same time, according to different sources, the buildings and the construction sector as a whole consumed 32% of global energy and was responsible for 34% of CO2 emissions. These figures clearly highlight that civil engineering is and will always continue to be at the center of the solutions to some of those great contemporary challenges. There will be no climate transition without civil engineering. There will be no resilient cities without civil engineering. There will be no sustainable mobility, water security, decent housing, or territorial adaptation without civil engineering. One dimension that I would like to emphasize today is the maintenance, renewal, and adaptation of existing buildings and infrastructure. For many years, the public narrative focuses mainly in new construction. Naturally, new construction will always continue to be necessary. But increasingly, our great challenge is also to care for, assess, monitor, strengthen, rehabilitate, and adapt what already exists. Buildings and infrastructures are aging. Demands are increasing. Patterns of use are changing. And the conditions for which many of these assets were designed and built no longer fully reflect our current knowledge, nor the demands arising from extreme events associated with climate change. Europe is warming faster than the global average, and climate risks are already a growing reality. Between 1980 and 2022, economic losses associated with weather and climate-related extreme events in Europe were estimated at around 800 billion euros. In Portugal, this winter, extreme events remind us once again that the resilience of buildings and infrastructures is not a minor issue. It is a matter of safety, economy, protection of people, and continuity of essential services. Following these events, an investment plan of 22 billion euros over the next decade was announced, aimed at strengthening resilience to climate challenge and other systemic risks. These developments reinforced an essential idea: civil engineering must be increasingly present in preservation, risk assessment, planning, and public decision-making. It is not enough to react after a crisis. We must anticipate, assess vulnerabilities, invest in maintenance, incorporate climate scenarios into our design, as well as in asset management. And you should explain to society that maintenance is not an invisible expense. It is one of the smartest ways to protect lives, heritage, and public investment. This is where cooperation between our institutions can play a very relevant role. Portugal and the UK have strong technical traditions, complementary experiences, highly qualified professional communities. We have Portuguese and British companies working internationally. We have many Portuguese engineers working in the UK. We have many British engineers involved in projects in Portugal and other European countries. And universities, research centers, consultants, designers, contractors, and public bodies that can all benefit from a clear and closer collaboration. I would therefore like to make a very clear point, as our president asked me to refer. The Ordem of Engineers is strongly interested in deepening its institutional relationship with the institution of civil engineers. In particular, we believe it will be very positive to discuss the possibility to formalizing a recognition and cooperation protocol between our institutions. Such a protocol could identify concrete areas of common interest, could value professional careers, could facilitate cooperation between civil engineers from both countries, and could create as well conditions for greater mobility, trust, and mutual recognition. The Ordem of Engineers will be very happy to discuss this possibility with rigor and institutional commitment, and to prepare together with you, I see a proposal that could eventually be considered later and signed by our institutions. I would also like to refer the European Council of Civil Engineers. The Order of Engineers follows closely the European work developed in the field of civil engineering with great attention. We believe that an active presence in European structures is essential to affirm civil engineering and to strengthen cooperation between peer institutions. There is also another critical challenge for the future of our profession: attracting, retaining, and valuing talent in civil engineering. We have been just talking before the beginning of this meeting, but we recognize that we really need more young people in civil engineering. We really need to attract qualified and motivated talent. We need to value the profession socially and economically. And we need to show that civil engineering is not merely a traditional field of engineering. It is a key profession for our society. Decisive for sustainability, safety, innovation, and quality of life. In Portugal, according to recent numbers, 84% of the employers declared difficulties in finding the talent they need, particularly in technical and sustainability-related areas. We may agree among us that civil engineering plays an essential role in society, but we have not always managed to effectively communicate our role. We must be clear, showing to young generations that this is a profession we propose with clear objectives and at the service of our society. We must also work with universities, companies, public bodies, and professional associations to ensure better conditions for professional practice. To ensure as well continuous professional development, recognition of technical competence, and fair appreciation of engineers' responsibility. The quality of engineering definitely depends on the quality of engineers. And the quality of engineers depends on education, ethics, experience, high standards, and professional recognition. That is why institutions as the Order of Engineers and the Institution of Civil Engineers are so important. We are not merely representative bodies. We are guardians of a professional culture based on competence, responsibility, public service, safety, and trust. Dear David Porter, dear colleagues, this bilateral meeting is an excellent opportunity to share experiences, projects, and visions. We thank in advance the colleagues who will present their work and contributions, which certainly will enrich this meeting. I hope that this meeting will also be a starting point for new forms of collaboration between professionals, companies, institutions here represented. To conclude, and on behalf of the President of Order of Engineers, Fernando Almeida Santos, I reaffirm our willingness to deepen our collaboration with the Institution of Civil Engineers and to work together to promote and to value civil engineering. Because the challenges ahead of us are too great. We need knowledge, innovation, and strong links among our institutions. We wish you all an excellent meeting. Thank you.
Thank you for those words. It's amazing the overlap that there is between what you have just said to us and what I'm prepared to say. And we didn't align the speeches beforehand, we genuinely didn't. But what you said in terms of the big issues facing civil engineering really resonate with me and resonate with the institution of civil engineers. So I want to first of all thank you for your kind welcome to Porto here and to Portugal, and for the words you've delivered on behalf of the President of the Order of Engineers. I really appreciate that, so thank you. I'm delighted to be here as the 161st President of the Institution of Civil Engineers. It is a huge honour for me to be the President of ICE, and I still have to pinch myself every time I say that, to make sure that actually is true, that I am the president of the institution, because I've been involved with the institution now for 27 years. And whenever I was thinking about my presidential theme, I came up with this tagline of you, me, and ICE. You, me, and ICE. And what I do to different audiences, I talk about you, me, and ICE in a slightly different way because I want it to be relevant to the listeners. And so for you, I often talk about finding your place in ICE. That feels a bit wrong tonight because there are other people here that are in this room that aren't ICE members or that are online that are not ICE members but are engineers and are involved in our profession. So let me widen it out to find your place in a professional body. There's real value in being involved with the professional body. That has been my experience over the last 27 years of being involved with ICE, because it has enabled me to develop my technical skills and to interact with people who taught me more about how civil engineering and infrastructure works. But it's done a whole lot more than that for me, because it has helped me to build my professional network, to get access to people that in the ordinary way I wouldn't have interacted with, that it gives me that opportunity to really develop lots of skills, not just my technical skills, but the other skills that we need to be really good engineers. And you've touched on them, Roberto, in terms of that communication to the society and to what I'm talking about in my presidency here, to that non-technical audience, how we can explain the real value of what we do in civil and infrastructure engineering to society so that they really get what we do as a profession. So find your place in your professional body. And that's not just a once in time activity. It's not just a case of joining and saying you're a member of ICE or you're a member of the Order of Engineers. It's a continual process. Continue to find your place. Look for that next opportunity within your professional body, and that'll give you the opportunity to give back to your professional body, to give back to your profession, but also to inspire the next generation of engineers. We need more people into our profession, as you have outlined here in Portugal, but it's the same story right across Europe, and it's the same story in UK. In fact, in many countries across the world, it is exactly the same challenge that we're facing of how we can get the next generation of civil and infrastructure engineers to study the correct academic qualification, to then take that academic qualification and apply it in the workplace, to become involved in a training scheme, and to move forward to become professionally qualified engineers. So by you being involved in your profession, you will give back. You will help inspire that next generation of civil and infrastructure engineers. So please continue to find your place in your professional body, because that will help bring forward that next generation of engineers that we so badly need. So that's the you piece. For me, I often then pick on something from my career that is applicable to the audience. And in this case, I want to pick up on what is Roberto already mentioned about the communication. Because I think that as engineers, we're really good talking engineer to engineer. We're pretty good talking engineer to other professions, particularly those that are within the built environment. But the real challenge for us is to talk to the non-technical audience. And the reason why I really want to reflect on that, or to get you to reflect on it, is for exactly the reasons you have said, Roberto, in that we need to explain the real value of the infrastructure that we provide to society. Not just in terms of what excites us as engineers, about the size of the rebar and the strength of the concrete and the structural form. That's all hugely important, and we need to understand that. But actually the users of our infrastructure, they really don't care about that. What they really want to know about is whether the service will provide a reliable, safe service to them, whether it will provide the service that they are actually expecting. So even on the journey here on the metro, I looked around in the metro car, and I was looking out through the window, and I was admiring the civil engineering, how the engineers had made the metro fit in with the city, and how at some stages it was above ground, and how at some stages where there was important buildings, they put the metro underground, and how they, in order to make that transition work, they had these lovely retaining walls, and they had soil nails in where there was unstable ground or rock, and then there was the signal system, and how all those track systems all came together in order for the metro to work. And then whenever I looked around the carriage, I was the only one admiring that. Everybody else that was on that journey today was more interested in where that train was taking them, where that metro was taking them. They were interested in what was at the other end, including, I have to say, all the civil engineers that are here. Because what they were doing was doing what human beings do. They were interacting with each other. They were talking about what they had for dinner, how they were going to get here, who else they were going to meet. They were telling other stories. So even the civil engineers use that service. And in many ways, then, the infrastructure that we provide is invisible. I don't mean you can't see it, but actually the physical form of it is largely invisible, because what people actually want to know about is the service that infrastructure provides, how they can get to the other end to come to an engineering knowledge session like this, how they can get to their place of work, how they can get to go and visit their loved ones, how they can get to go to the hospital to get that treatment that saves their life, how they can get to the airport in order to go on their family holiday so that they can enjoy time together. That's what people are interested in. And as engineers, we need to realize that. We need to understand that, yes, we need to be technically brilliant so that we have the infrastructure that society needs, but we need to change the way that we communicate that value of that infrastructure. And I think if we do that, that will start to get the message around about the importance of our profession and the central place that it plays in our society. That's you, me, and I'll finish off by talking a little bit about ICE. So ICE is the oldest professional engineering institution in the world. It was formed in 1818 by a group of young engineers, 8 of them, that came together in a coffee shop in London, in Fleet Street in London. And they recognised that by coming together and talking about some of the engineering challenges that they had, they were better engineers. So tonight's meeting is entirely in that spirit, because we're going to hear from other engineers about projects, and we're going to learn about some of the challenges that they faced. And we can then take that learning away and apply it to our own projects and to the activities that we carry out. And once I can talk about how ICE formed in 1818 and how over that 208-year history it has gone from those 8 young people in that coffee shop through to almost 100,000 members in over 160 countries across the globe. Interestingly, ICE, even with that history, even with that huge membership, we don't have all the answers. But what ICE is brilliant at doing is working in collaboration with others in order to find those answers. And so your point about collaboration is exactly the sort of offer that ICE is very interested in. And I'll be delighted to have that conversation with you, because we need to work not just as old and established and very proud institutions ourselves, but we need to work in collaboration with others so that we can genuinely provide the infrastructure and the civil engineering projects and the maintenance and management of our assets for the benefit of society. So thank you for your attention. Thank you for your welcome here. Thank you for listening to me. And don't forget you, me, and ICE. Thank you very much.
Good evening, ladies and gentlemen. My name is Julia Tarasińska-Sochacki. I'm a bridge engineer, and I also lead the Bridges and Civil Structures team in Germany for Europe. Today I'm going to talk very briefly, because I'm on the clock, about the design of the replacement Moulin Bridge in Berlin. Middle is the center of our buildings. So, about the so in 2021, Europe won a design competition for the replacement bridge of the Moulin Bridge. The existing bridge is located in the very center of Berlin. It crosses our beautiful Spree River, and it connects from the east-north to the southwest of Berlin. It's like aorta road B1 of the city. It's a very heavily trafficked, heavy traffic on this road. So obviously, a big challenge to design and build in such conditions. It is also, it's not visible here, but on every corner, the bridge is surrounded by buildings, a lot of heritage, and also a weir and docks. So on a curve as well, just to make it more complicated. So the existing bridge has been, after many assessments being done. So essentially, at some point in 2017, the cracks found on the bridge were being a little bit too big, and the whole assessment process started. They went for a lot of levels of assessment for the bridge, and eventually classified as no longer able to carry the full load that it was back then carrying. So as you can tell in the photos, the road, the traffic, the space on the bridge was restricted, not only for the vehicles, but also for pedestrians. There was I don't know if I have a photo that way. So there is a lot of visible corrosion on the bridge. So parts of the concrete have fallen off. And another thing that has brought a lot of concern was the fact that the bridge built in 1968, they used a Henningsdorf pre-stressing steel. So it's a concrete box girder pre-stressed. And this steel has been found very prone to corrosion. And I don't know if some of you have heard of the collapse of the Carola Bridge. That bridge used the same steel in the construction. So it is a well-known problem that needs to be, So a lot of bridges in Germany that have used that steel are currently being replaced. So as mentioned, there was a design competition in 2000, and in 2021, Europe, together with architects from Denmark, Toda Architects, won this competition. This is the relative view of how the bridge is going to look like once it gets built. The whole concept of the design and the future proofing of the bridge was to design it for a few stages. So with the change of the means of transportation, it has been identified, or the wish of the public, of the residents in Berlin, was to reduce the vehicle traffic and change the functionality of the bridge. So in the future, it will go through two phases. We will initially reduce the amount of car lanes from 4 to 2 on each side of the bridge. We will introduce a wide and safe cycling path and much wider space for pedestrians to enjoy the bridge, also stay on the bridge and enjoy the views. And in the future, the idea is to bring the public transportation, so tram on the bridge, reduce the car traffic to just one lane per bridge, and encourage people to cycle, walk, and use public transportation. So moving on, so here's a couple of impressions, and I will be talking a bit more about the constraints. So as you can see in this photo, this is looking east. Here is our TV tower in Berlin. There is a Nikolai filter. We have a We have Alta Münze. All of these buildings on the sides are heritage, they are listed, and they are right next to where our abutments, where our supports, where our connections onto the bridge are. So there is a lot happening in the ground. I haven't mentioned, but this is the existing bridge is the third bridge in that location. So we are building the fourth one. And there is a lot of history in the ground as well. So the design of the sanitary works and strengthening to the excavations was just like a different dimension of complexity to try to build in such a close neighborhood of heritage buildings and structures. Also, this is part of the docks and the weir construction. So the weir is on that side, finishing somewhere here, and towards this, toward the south, this is where the docks are. So we obviously have to design the bridge or design the construction of the bridge in such a way that we do not close the navigation channel for during most of the year. So we are allowed to close it during the winter times, and obviously we have to keep the traffic on the bridge moving throughout the whole construction period. A little bit more about the space on the bridge. So the design won because of the space that we created on the bridge. We are planning the longest timber bench in Germany, like in one piece, which is something that Berlin is especially proud of. So as you can tell, we have compressed the traffic, we have created a lot of space for the pedestrians with the views for both sides. It is also a very pretty part of the city. It's right next to what we call a museum island, and you have a view of a lot of heritage buildings around. Another thing we did, we've opened up the space underneath the bridge. So if you can remember, the existing bridge has a wall the substructure is basically a concrete wall closing the space, making it a bit more claustrophobic. So we've opened it up, introducing the faux-shaped columns and adding a bit more length from the angles. So here's a little bit about the engineering behind the design. So this is a composite steel concrete continuous beam. So our main beams are steel box girders with a concrete plate on top. These lines do not show a transverse beam. This is just the cladding underneath the bridge. So the structure itself is just the box girders and the concrete slab spanning between them. Why the cladding? Not a very popular idea nowadays because of the maintenance, but actually this is coming from the approval design, which has developed significantly. We are currently about to award a contractor with the design. So the amount of utilities that you can see has probably doubled. We have about 30 or 36 service utilities providers or owners who each one of them wants to have a pipe, a cable, a space under the bridge because of its location. So that has been a big challenge, trying to fit it all. And that's why the cladding, so to make it a bit more aesthetically pleasing for the users of the riverbanks and also the tourists that use the navigation channel. So the width of the bridge, the existing bridge is 44.5 meters wide. We are reducing the traffic. We are expanding the place for the pedestrians, but we are still reducing the width of the bridge to 38.33 meters. And yeah, I think that's about it. Here is just like a vision of the 3D model of the new bridge that we have designed. As mentioned, we are completing now the issue for construction, and the contractor is due to be awarded the contract in end of May to start with the foundation works. yeah, a couple of details. So I've mentioned that before. There are two very important and very challenging constraints from the client and from the third parties. One is to keep the traffic on the bridge or on B1 road going. So for that, when planning the construction sequence, we had to assume that only half of the bridge will get built, and then obviously the second half of the bridge will then, once the first half of the bridge is built, the second one will be demolished. Luckily, they are separate structures, so it's two separate superstructures that are asymmetrical. So this is relatively easy, although they are very close together. So there is a lot of like tolerance, very little tolerance for the contractor, especially when it comes to building the kappa, which is the edge beams of the concrete, because of obviously concreting works, they have to be done in situ in Germany. Another big constraint was the navigation channel. So this is a very busy navigation channel. The locks are here, and as mentioned, we can only close the navigation channel during the winter months. Obviously, the construction is going to take much longer, so the plan is to use the full closure was to demolish the bridge, and now when we start with the foundations, we will be using a part closure. With the part closure, it was also not an easy thing, so the waterways authorities made our life really, really as difficult as it can be. They have asked us during one of the meetings to provide what they called the ship maneuvering lines, to prove that a 90-meter long barge can get through the dock, come out and move underneath the bridge whilst we have a big pile drilling machine on a pontoon next to the. So we've managed to do so. It was not an easy thing. So as mentioned, where are we now? This is an old picture. So the bridge is actually, the first half of the bridge is demolished. There is nothing here. There are some works being done, so some renovation work being done on the molar, and we are about to award the contractor with the new build of the first part. And we will see how that goes. That's it. Thank you very much.
All right, so good afternoon, everybody. You are very much welcome. I have so little time that I'm going to go speedily into my presentation, but my connection with the institution go back many years. I studied in London, and then I was involved very much with the institution as the Vice President, President and Vice President of the European Council of Civil Engineers, because the institution of the European Council of Civil Engineers is still nowadays, on the legal point of view, is based in London. Legal and financial, by the way. Well, I wrote 10 seconds for each slide. So the history will be also very speedy. But when considering the challenge of speaking of some structures in the north of Portugal, well, we came to the conclusion that the best thing I could do will go through the history of the bridges in Oporto, and then my colleague Renato will talk of two major structures that are worthwhile. So I've got 10 minutes for me, 5 minutes for him. Let's start. Well, I have more bridges, yes, just to be honest. And I start with the boats bridge. Well, the Rio Douro actually has played a very important role in our history in this part of the peninsula. In fact, the Moors always have difficulty in staying in the north of Oporto. They were sometimes coming in, but they had to retire. So because crossing the river was difficult, for sure during winter time. And it may be said, this is not an historical truth, that Portugal came up to exist because of the River Douro. When River Douro somehow separates us from Lyon, Spain was not. Spain was just several counts, and this part actually took the name from this city, Portugal. Cale in Latin means place, so Portugal actually is due to this city, and we exist thanks to the River Douro. But the River Douro has always been very difficult to cross. And the first initiative that was took over, I jumped one slide, no? Okay, so no, you're up there. Was in 1396 when, well, we are very fond of the people living on the other side of the River Douro, that is nowadays Spaniards. Before they were the people from Leon. We are very fond of them. Yeah, but friends sometimes discuss. And in 1369, an army had to cross the river to help and counterbalance the invasion that was coming from Galicia, nowadays in Spain. But the bridge was built and taken out, and only in the 19th century, the first so-called permanent bridge was built. Why I wrote semi-permanent? Because in winter, the bridge had to be dismantled because of the floods. The speed of the water in Porto under flood is really unacceptable for any structure. Well, at least for sure, like a boat or bridges. It's just a note that took 2 years to build. Well, unfortunately, with that bridge, we have this tragedy when the Napoleon troops came from the north, and the population tried to cross in a hurry, and well, the bridge was not well prepared to withstand, so several thousand people was drawn in the river. By that time, people didn't know how to swim. Something that we forget. Nowadays, we are supposed to swim, but this was not the case in the beginning of 19th century. So only in 1848, the first bridge was built, a suspension bridge, similar to many others built around the world. Porto was entering a very important phase on the second half of the 19th century. Porto developed very much, as I said before, very much thanks to the British that came over here, starting industrialization and taking our port wine to be sold everywhere. Thanks for it. It's a great achievement. So this suspension bridge. What is beautiful with this bridge is also the drawings. The drawings are really to a detail. More than half of it to explain the materials, the pieces that had to be put on the bridge. Nowadays we do much less. Well, the contractor does it later on. But we are not obviously spending time with these drawings. This is already a photograph of that time. The problem with the bridge was that it was like the Millennium Bridge, and it was difficult to cross with some wind. So apart from the durability of that iron, of those cables, was not good enough. Anyway, the city started to develop a lot, as I said, the second half of the 19th century. So we had to have a cross down here and also another up there. But a few years before, the train was coming from Lisbon, had to cross the river, and then, well, before we go, just some pictures of floods. It was in 1860. These were more recent. I remember this flood in 1962. Now the rest of these floods, because many dams were built, so somehow, in spite of the of the climate change, we are able to control a bit more, better the river. So it was in 1877 that we had this big bridge built by the Gustav Eiffel Company. He came up with this splendid work of art. The officer was actually the engineer, the civil engineer who did the calculations and the drawings. The drawings, because the calculations were graphical, and the precision in which those drawings were made, this sort of graphical drawings, well, not so young people already don't know at all, because now it's not used anymore. Anyway, this bridge is, this bridge, the way it was built, and built in less than 2 years. Less than 2 years. Gustav Eiffel was no doubt a great entrepreneur. He was a civil engineer, true, but he became an entrepreneur full of capacity, initiative. So this bridge was built in less than 2 years. Amazing. This was never done after that. So in spite of the arrival of electrical machines, etc., this was done only with human force. But this construction, cantilever construction, really is quite something. I don't know why Robert Meyer comes here. Oh, I know, I see. There is a comment that any vote on internet, which is the most beautiful bridge in the world, the winner is Robert Meyer San Benito Gabriel Bridge. It's indeed a beautiful bridge in an outstanding location, quite obviously. But the comment is that in this bridge, we have 3 inches. But in the one Gustav Eiffel and Selig did in Oporto, we have actually just 2 inches, which it means either a hyperstatic structure, and to calculate hyperstatic structures before we had computers was quite something. Quite something means impossible. Quite impossible. It was quite impossible. But it was possible by proper engineering and thinking, understanding of the behavior of the structure. So the bridge was a railway bridge. And then, sorry, I'm not mastering very well this little mouse. Less than 10 years after, this bridge was built next to the suspension bridge. Already built, the suspension bridge was demolished only 2 years later. This bridge really was designed by Theophil Selig. Theophil Selig was partner of Gustav Eiffel. Gustav Eiffel took most of the credit. Theophil Selig didn't like that idea, so he decided to leave the company. He joined a Belgian company, and he won the competition for this bridge, still there. Probably you will visit it. There it is. It's spanning 172 meters. We cannot go into much detail, but they were always seeking, well, they had to build, they wanted the bridges near the city for sure, but they were seeking the location where the river was narrow. Well, I will jump 4 meters, maybe running, but 4 meters and 20, that will be impossible. Any extra centimeter is hell and a big challenge. So, but indeed, this bridge took 5 years to build. Probably Gustav Eiffel laughed about the time it took to build the bridge. But anyway, still there. Both of them are still there. There it is. The increase in traffic and economic activity on both sides was immense. By the way, the port wine was taken down the river, and the cellars are on the left side, are on the other side. So the wine is here, and the population, most of the population is there. So I don't know whether they were crossing because of the wine or not, probably not. But anyway, again, the same hinges, it's also an arch with 2 hinges. And then, well, 19th century went, not just Portugal. Portugal went into a very difficult period, the end of the monarchy, and then 20 years of chaotic republic. I'm not criticizing the republic. It's just the fact that it was a bit chaotic. It is understood that the monarchy is a stabilizing factor. By the way, Mexicans tried to do it with the Emperor Maximilian, but then a Republican killed Maximilian, and I'm afraid Mexico, a super country, is always in some difficulty of well, let's move to bridges and leave this difficult subject of politics. It was in 1963 that this bridge was built. The designer Edgar Cardoso. This bridge is located in a fantastic scenery. We have the mouth of the river down there. This bridge is really, it was a world record when it was built. But world record is just a matter of curiosity, nothing more than that. And for the Guinness Book, they need to publish new editions, so they need world records. It's actually made up of 2 arches. The arches are very strong arches. They are self-supporting. They are 4 meters thick at the bottom and 3.5 meters at the top. So the way it was built with a temporary steel arch, then they did the concrete on top, then they moved the steel arch to the side, and they did the second concrete arch. And after having those arches, self-supporting and very strong, they built the deck with a normal scaffolding, as we see in here. There it is, the bridge in a super location. It's really outstanding, this bridge. And it was in 1991 that we have had another bridge, a railway bridge that where the train was taken from the Maria Pia Bridge, the Eiffel Bridge, and moved to this bridge, which is the one that was most of the time in here. There it is, down there. On this kind, and being a railway bridge, is still a world record, 250 meters long, the central span. Beautifully done. It may be a joke, but Edgar Cardoso said that the idea of the columns came when he was preparing to eat a carrot. And so we got the idea, whether it is true or not. It is an interesting story. It's quite elegant, this bridge, no doubt. And the construction is a cantilever system, nowadays very common, 250 meters. You have longer spans, but not in 4 railways. There we are, next to the 2. The train was going on the right, and now going on the left side. This bridge is because we have Edgar Cardoso here on the left, and Fritz Leonard, which is obviously a well-known bridge designer, and I'm one on the shade behind. That was 40 years ago, I'm afraid. Oh, yes, great, 40 years ago, I lived longer. And there we are, the bridge, the St. John Bridge. And then it was already on this century that we were able to have another bridge, the Infant Dominic Bridge, a road bridge. It was built so that cars could be taken from the Louis Bridge, where the metro now operates. This bridge was actually based on Robert Maillart's concept of a very shallow arch, thin arch, very thin arch, and the arch is not self-supporting. You will decompose if let alone. So it is the deck, strong decks, that keeps the arch in position. And if he is in position, then he gets only compression, 95% compression, and then concrete is an excess material. The designers actually are nowadays working one of these companies. Sorry. It's just a nice picture. In here, because the arch is so delicate, could not build in front of the deck as he was going to in construction. He had to be hanged from the deck, so the deck was ahead of the arch until they were united and finally closed. So it was quite an achievement, and providing some beautiful pictures. Took 3 years to build, so Eiffel was much more successful. The construction was possible because with temporary cables and temporary struts, we actually got a truss. And the truss is the most effective, efficient structure. After being united, there it is when the two sides are already connected, but we still have all those cables and temporary struts. Well, like one in here, and the cables, they were all taken out. It was quite well. Sorry, it's quite when this temporary column was taken down. The contractor decided to do it on a holiday over summer, because this always, if anything goes wrong, is better. All the newspaper and TV are on holiday. Just in case nothing happened, it was a success. Amazing. Oh, sorry. Well, let's go ahead. Time is running short, and I don't want Renato to be without any time. And I still have a couple of to go. There we are in the center. So this bridge is in the middle of the two iron ones. The Eiffel in here, and the Selig, the other one up there. The Arabia bridge is on the far up, a bit difficult to see. And now it is under construction, this bridge. It is starting. If you go there, you see already that it is under construction. Will be ready hopefully in 2028. The designers are those companies over there, the engineers and an architect involved. It's an enormous bridge. It's got a span of 450 meters. 450 meters. Will be an immense bridge, no doubt. Well, we're not going into the detail. It's not exactly an arch. That's more like a frame. Although we have that shape of an arch in the middle, but it's mostly more a frame than an arch. Construction is well known, with temporary columns and stays for the construction, the progressive construction, and here the picture of the bridge. So thank you very much for your attention. I hope you
Good afternoon. I will try to speak only a few minutes because we are late. Sorry. It's fine.
No. Oh, no, take it out. No, I said thank you, and
So I will just try to speak a few minutes about two major structures that we have here in the north of Portugal. Both structures that are, we believe, a good example of exposed concrete. One in white concrete and the other one in ordinary grey. The first one is the Casa da Música here in Porto. The architect is Ren Kulas. In the competition, Ren Kulas joined ARUP and also our former company AFA Associados, and the proposal from Ren Kulas was selected with that very unusual shape. At the beginning, the idea was to have something that was not in concrete, be some steel structure with some transparency, but the idea of white concrete was very welcomed by the architect. In fact, he didn't, let's say, think about the white concrete from the beginning, because in the north of Europe and maybe the skills and the labor need to do good exposed concrete nowadays and at that time was not so, let's say, common. But here in Portugal, fortunately, we had it. I think we still have that knowledge, and the idea of changing it to white concrete was very welcome by the architect. We don't have time for much thing, just to explain. We have more or less 30,000 square meters of construction. What we see above ground, let us say, is only a part of the building. The building is a concrete shell, entirely showing the structure, and that was also the idea since the beginning, to show the structure, and the structure will become also the main architectural element, or to say the main architectural sentence that would be shown to the public. The shell acts together with all the slabs and with two major inclined, sorry, there is something strange here, two major inclined columns that help that shell to be stable. And then inside there is a lot of other minor structures, inclined columns, smaller columns. And here in this 3D model of the building, it's clear to say how it is very demanding all this. The stereotomy of the exterior was also imposed by the architect, and everything that, like I say, is concerned with the quality of execution was a major, like I say, issue since the beginning. The result, I think, is quite good, as you see that volume in that place, and the quality of execution, and also the difference between the architecture of this new element and the consolidated other buildings that are. I think it's a very nice example of what can be done when architects and engineers join and have that, let us say, collaboration that leads to this result. The other example is the new Braga Stadium that was built for the Euro Cup of 2004. The architect is Eduardo Sotomora, Pritzker Prize, Portuguese Pritzker Prize. The idea was to build at only a two-stand stadium with a roof that should be as thin as possible. So the idea was to have that big excavation on the rock in one side to create like an amphitheater that could be used to have one of the stands, and on the other side cantilevering the other stand, helping also to anchor the roof cables and to be stabilized between the self-weight and the force of the cables. The similar structures or suspended roofs we have many examples. The Foster Dulles Airport in Washington, also the Portuguese Pavilion in Expo 98, and inspiring structures are the old bridges in the South America. So we have a roof that spans 202 meters, a roof span. We have, more than 90,000 cubic meters of concrete, everything also exposed concrete, the excavation on the rock, it's automatic and ready. The excavation on the rock and the stand. We have one stand that is directly anchored on the rock, and the other one that is cantilevering. And everything is exposed. Not only the concrete itself is exposed, but also all the details, all the connections, everything that could have some technical meaning. The architect choose to expose everything. Even in some cases, the foundations and the structure, the anchors, everything is exposed in this building. The main, let's say, issue about this stadium is the wind stability of the roof. There was since the beginning maybe the most demanding engineering issue of this. Several models were done to study the behavior of the roof. At the end, some discussion even during the design between the different models or different results from models, between the deterministic analysis and the stochastic analysis. But at the end, it was proved that the roof is stable. It was monitored and is still monitored. So the result of like I say, this issue about structures and architecture and showing everything that has a structural meaning in these two examples, I think it's a good example how the collaboration between architecture and structural engineering can give, let's say, this excellent result.
Thank you very much. I'm in big trouble now because those were some really good presentations. An amazing new bridge, a fantastic history lesson, an auditorium that looked like it landed from outer space, and a really cool football stadium. So I'm John, I'm from Copenhagen Metro, and I'm going to tell you a little bit about what we're doing with sustainability, innovation and carbon on Copenhagen Metro. I could have given a presentation that's really technical, but you've just seen some really cool technical stuff, and I can't hold a candle to it today based on where we are. And instead of telling you what we're doing with innovation and sustainability, I'm going to attempt to go through how we're doing it, which I think is a bit more helpful. So here goes nothing. That's in case I forgot to take Copenhagen Metro. The first one was carbon on metro projects, but it's the Copenhagen Metro where I work. That may be too small to read the details, but each slide should have some context if I can always remember it. I'm going to do 10 seconds per slide to keep up, otherwise we're going to overrun. The important thing here is who owns us. So Copenhagen Metro is owned jointly by the City of Copenhagen, 50%, the City of Frederiksberg, which is like an enclave in Copenhagen, and the rest is owned by the state. So just like 58.4.1%. It's not just that we work for these guys, those are our owners, but we work with them. And this is really important. We have a really, really good relationship with our owners, and they are the guys that help us get things done. And without them, we couldn't do anything. So we owe them a big thank you because they allow us to do what we do in such an amazing way. A very short history lesson. I'm going to skip the map. If you've not been to Copenhagen, the colour lines are the metro and the grey lines are not the metro. But that's where we're going. These metros are fairly new. I can't do a history lesson from 150 years ago, but I can do one lesson, which is the first one was in 2002 and the last one opened in 2024. So why is this important? This is important because we are about to embark on the 5th metro. That's the 5th generation in Copenhagen. And this is all in not just living memory. We have a team that delivered this in Copenhagen. It's not just that we did it. We know the people that did it. They are still sitting in the desk around us. So this isn't my first rodeo. I was involved in M3 12 years ago. The guys from M1 and M2 that were there 25 years ago, they sit by our sides. So we do have the knowledge of what we did last time, so we can learn from it for what we did this time. That's important too, for something I'm going to come on to a little bit later on. A few other things, apart from building a world-class metro, I could tell you about the way we run the metro, but I'm going to skip over that because we're running short on time. But I'd like to say two things. Firstly, we're 24/7 operation, which is something quite special. Secondly, our customer satisfaction is at 98% and operation stability is at over 99%. If you know any other metro that's doing that, let us know, because we need to learn off them, because our targets next year are higher. We don't just do the metro, we've also opened a light rail system in Copenhagen. So this one opened, the south half opened in October last year. The northern half opens sometime this year. Don't pin me down on it. I'm on a live video, I'm not going to give you a date. Something else we do is, because we work closely with the communer, we help them do their planning. So when you build a metro, you don't just build a metro and let the city go around it. You do that development and the planning together. So as well as design the metro, we've got a planning team that actually help work out what it's going to look like when. And I could show you a whole bunch of slides that show you what metro lines 6, 7, 8, 9, 10, 11 will look like and how the city will build around them to develop the city. So we have a Metro 2070 plan in the pipeline for what happens next, and then next after that, and next after that. Because we want to build a city, not just a metro. We're obviously a key part of that. So, just a little bit about the way that we help build the city around. This is a photo taken probably in a hot air balloon, isn't it? 2002. This is my office. That's my desk just over there. So this is when the metro opened first in 2002. This is our maintenance centre that's at the end of the metro line. So you've got the city over there. This is south end of the leg. So that's 2002. And the way this is financed is because we're going to use this plot of land to go and build and generate and fund the metro. So lo and behold, that absolutely happened. That's not a rendering. That was a couple of years ago. So that is what it looks like now. So roaring success. We've got a big stadium. We've got a sports arena there. And this is mixed use. It's residential. It's businesses. It's offices. And it's been a roaring success. It's fantastic. So based on that model, we're also developing the M4 up in the north of town to do something similar, based on the same sort of funding model that we use the money we get from other things to fund the metro. The system works. Enough about that. I want to talk about M5 Metro, innovation and carbon and sustainability, all in one big thing. I joined the metro about 2 years ago. I used to be a consultant doing metro design, and I used to do lots of little studies for them to help them deliver design and build a better metro. They had an idea that the next metro, bear in mind the last metro is 2024, the next metro should have half the carbon footprint. This is doubled down on by our CEO, the chairman of our board, that said, we can do this. If we might have to take some risks, but we will make sure we take the right risks, the right level of risk, and those risks will be low. We need to learn and make sure those risks are acceptable. So don't go crazy here, but we can do it. Let's educate ourselves and do better than last time. A bold statement, but we are well on our way to doing it. So I'm going to try to show you how before I get thrown off the rostrum. A little bit about the M1 and M2. This is a sketch that was done in a cafe in Paris in 1996. Let's go and do a really simple metro. It's a watertight box. It's got some escalators. It's got some skylights, and the metro goes through it. Really simple, modular design. If you've been to Copenhagen, it's quite a cool metro. It's quite simple, straightforward, easy to navigate, and it was a roaring success. In fact, the next drawing show this is what it looked like. So you had the sketch from '96, and this is the actual technical drawings of our metro line 1 and 2. Great, fantastic. Let's build some more. And when we did the metro line 3, the objective was more of the same, please. It actually says that on the design brief. We want more of the same. We like it. Everyone likes it. Let's do that. The problem with more of the same, the problem with modularization, is it's not optimization. So if you do all your stations like this, which is what we did 20 years ago, they're not necessarily perfect in terms of the carbon footprint and sustainability, unfortunately. So what we thought when we're doing the M4 and M5, we have to do it a bit more optimal to make sure we get those carbon footprints down to that incredible target of 50% less. So firstly, those stations weren't all the same, but we've actually been, as we've been expanding, we've got a suite of different metro stations. And we've been using these to make sure that we choose the right one for the right place. And if we can use one that is shallower, we should, because from the left to the right, the carbon footprint gets less and less and less. In fact, there's probably a sweet spot around about there. But this is important for choosing the right thing for the right job and not to do the same thing everywhere. So this is the plan for Metro 5, and you can see without the details, we've got 6 different metro stations. They're totally different. They're not optimized. They're not modular. They're optimized for each different location. You've got a really, really deep one that's like a shopping centre over here. You've got some semi-shallow ones here, but each of them are suiting the geology. I wish I had a geotechnical long section, but I forgot to put it in, but we go up and down to make sure we are as shallow as possible. It potentially is a bit more risky on the tunnelling, but it saves so much. And modern tunnelling technology is up there that we can do this. We're not worried about it. It's good. I'm going to skip over that one. I quite like this one because we're going to put some more bicycle parking in. We're going to use the space between these boxes to utilise it. So it's not just digging a big box and making a hole and filling it back in again. We're taking full advantage of the space that we create. So the cycle parking, if you've been to Copenhagen, we're full of bicyclists. So we're giving the people what they want. That was a request from the Copenhagen city. So carbon. I'm going to whiz through these. Carbon, it's a big deal. So here's a footprint of the carbon from the countries around the world. Denmark is not the worst sinner here. In fact, I've got the UK on there. Can I see Portugal? Can anybody see Portugal? The point is, if you can't see it, you're not doing too badly. The point is, even though the UK and Denmark aren't the worst, but they're not the best. So we should try to do a bit better. When we're talking about the carbon footprint of a metro project, most of it actually comes from construction, which is probably known for most projects as from construction, not from operation. And out of that, most of it comes from the concrete and steel. I mean, this is rocket science, I think probably all know that. So when we're breaking this down, we are trying to take off that by half. That's the 50% saving. It's important to set these boundaries so you know what we're aiming for. It's not those other things, because the other things will come later. This is our target that we've established. So we're not doing it blindly. If you look at some of the other client organisations, they're setting similar reductions, and some of them have got different baselines. So the city of Copenhagen sets a similar 50% reduction in their carbon by 2035, which is kind of where we're aiming the metric. So it's not our idea, it's been put on us by the client to compete with other clients around the world. So you can do the detailed numbers, are we doing better or worse? By the by, we're aiming for 50 for the next metro. I'm going to skip over that for time. Yeah, here we go. So how do we do this? It's worse than that because there's loads of these. To do this, we've actually made sure that we measure the carbon footprint based on the way we did it last time. We can do that because we've got the bill of quantities from the last metros. So this is the trick. Our carbon footprint is linked directly to the bill of quantities. Oops, I've skipped. Yeah, so no, that's okay. It's linked to the bill of quantities so that we can measure it as we build it. So we had our matcher design in the old way from 2020, and then we said, okay, how do we get that down? So that's our baseline, and now let's look at changing things up. So this square here represents all the carbon in the project, and you can see that the bigger squares are the bigger carbon, and the smaller ones are the smaller bits of carbon. And it's a simple math that a small percentage of a big thing is a lot easier to do than a big percentage of a small thing. That makes sense. But simply it's the scale. So where you've got all the tunnelling is there. So if you say 1% of the tunnelling, that's worth way more than say 10% of the shafts. So it makes you focus on where's the carbon. It's a bit like going for the big fish and not just trying to catch all the small ones. So we can focus our energy to the right things. And we can break any of those down to if you're familiar with A1 to A3 is the sourcing, the A4 is delivery to site, A5 is your carbon on the construction site. So we've mapped it all. And when you map it all, you can work out how to save it, which is how we're doing it in a nutshell. So eliminate, reduce, substitute, compensate. These are traditional ways to go and help reduce your carbon footprint. I'm going to go. How am I for time? Cool. Innovation. So I run an innovation team, and we've been doing innovation studies for maybe 5 years now. The innovation studies have been looking at problem areas and drilling down to learn more about them to see can we do better than last time. So the trick was that if you can see a problem, let's scour the world and try to find a better way to do it. And the ways to do it are multiple. You can do it through. I'll skip through that. You can do. I'll get back in a minute. You can do it by just clever design. You can do it by using cool futuristic materials, or maybe you can do it on the construction site by saving it in other ways. But we're trying to turn over every single stone to see where we can find it, and that's what we did. We had over 50 independent studies, and by the time we're about to get a tender soon, there were 200 innovation ideas. And I'll clarify an innovation idea. It's something that we didn't do last time. That's our version of innovation. And it works because last time in 2024. So out of those 200 ideas, I can hand on heart say that 65 of them, it's about 30%, have made it into the tender document requirement as a hard requirement, which I'm super proud of. You may think, well, out of 200, is that good? If you look at how many were there and what they meant, it's our way of getting down to that 50% reduction. And it's phenomenal. We haven't built it yet, so we'll see how it goes. But as a hard requirement in the contract, we think they're doable. We don't think they're crazy ideas. We think these are all very achievable ideas because we've seen them done elsewhere in the world. They're not new. They're not from outer space. They're market ready. That we've seen the contractors that we spoke to. They've done it elsewhere. Phenomenal. I've got a few examples of how we're doing it because everyone says, well, what do you mean by innovation? All of you might say, that's not really innovation though, is it, John? It just isn't. Some of them aren't. Some of these are just good design. So you could just not build something. That'd be innovative. Just skip a station. Now that's just not giving you what you need as a deliverable. But by building shallower, that takes some technical know-how to be confident that you can build it shallower and the tunnelling can still work. So we've really pushed our designers. So credit to Ramble and Covey and Arup as our civil works designers. They've done a phenomenal job to really squeeze every inch out of that. I might call that good design, but I think they've really pushed themselves. It's great. So shallow stations, this makes a big difference. It also saves money. If you can build less, you build less. So that just doesn't save carbon, that saves the money as well. Brilliant. This is an innovation I like, but it's worth me holding on this one. The distance to the switch. So when you've got a station box, you've got a crossover just outside the station box. This particular idea came about from saying, if the transportation guys rethink the requirements of their crossover, it could be shorter. If it's shorter, the civil engineers can make the box shorter, and we all save. And they reanalyzed the train speeds, and they came up with a 30-meter saving. That's a 30-meter of a really deep station box that we're not building. So that's not building it at all. But that took collaboration between the transportation railway guys and the civil guys, who historically, they're usually on different planets when we're designing a metro. This was a big deal, and we've done it everywhere we can. The build less. Our current metro is on a system of viaducts when it's overground, and it's on these beautiful pairs of viaducts that run over to the middle section in Copenhagen. Now, one way to save 50% is to do that and just build one of them. That's cheating. So what we've done is we've squeezed our designers to come up with something that is maybe not quite 50% less, but a bit more elegant. And we think that this is going to work. Even if it's not quite like that when you see the finished product, we've got something that we know and it's tested that will be 50% less carbon. And that's fantastic. Again, you're saying it's not innovation, but you know what we're always doing as designers? We're doing copy and paste from last time. And what we're not doing here is that. We're trying to do it from afresh and get it right. I'm going to skip that one. That's just about using modern materials. This is quite brave to use modern materials because is it really, really market ready? We're only putting in the spec the ones that we know are market ready because a lot has changed in the last 5 years. It's brilliant. Some of the suppliers are coming up with the goods that will save the carbon. I'm really happy about that. Now, the trick is when we're going to be building it, we need to monitor it. Otherwise, it's all for nothing. So it's going to go. The project will go to tender this year. and get awarded next year. When we start construction, we've got to keep an eye on it. So otherwise, we can't say. So that's why the carbon footprint is linked directly to the bill of quantities. So when they're there building it, just like they're reporting on the cost and the quantities, they can also be reporting on the carbon, which is an excellent way to do it. Possibly one of my final things, electric vehicles. We're going hard on electric vehicles on the Copenhagen Metro. On our existing projects on the M4, we used some small electric plant. This is one of our electric kits on the wrapping up some of the station works. We're going to go a bit bigger than this. We're going to have requirements to say not just this many vehicles must be electric, but this quantity of energy consumption will be electric, or so I should say low carbon. Actually, it's not just electric. It could be I'd say the low emissions diesel as well. But we will set some requirements that mean that we are not just asking for what the market can handle, that we're hopefully pushing the market a little bit. So we're part of an initiative together with Copenhagen that we're trying to, instead of just see what the market can do, we're trying to lead from the front. So hopefully this will work, and we're hoping other clients will also say, well, if they're doing it, we'll do it. And by doing that, we will develop the whole industry by getting more and more low emission vehicles. That is all I had to say, apart from some conclusions. Sustainability is more than just carbon. And if I had more time, I'd talk about resources management, because in Denmark, we do not have very many natural resources. So sand and gravel is in very short supply. There's been discussions about using GGBS, but we haven't got any. So the way that we do this has to be, we are thinking about more than that, and we do have resource requirements in our tenders. I'm going to go through all of those because I've forgotten what they all said. We are on target for that 50%, we think. We've done a huge amount of it before we even get off before we go to site, which I'm hopeful that we can deliver on. So watch this space. The project goes to tender later on this year, and we say we open in 2036, but we'll know where we are way before that because we'll be chasing it all the way down. So feel free to ask me about anything about the project afterwards. I'd happily talk to you more about than just carbon, because it is not just carbon. But I thought for this, stick to the carbon. Thanks very much, everybody.
So I'm afraid you've got another John now, but the good news is I'm the last John before the drinks break. So, so I'm talking about CERN, the particle physics research laboratory. I used to introduce myself. I'm from the UK, civil engineer, worked for a tunnelling contractor for 10 years. My last job was Canary Wharf Station in London, and I joined CERN nearly 30 years ago for the Large Hadron Collider, and I'm the Switzerland country rep for the ICE. So I'll give a quick introduction about CERN, talk about our existing tunnels. One slide on tunnel asset management, so maintenance and monitoring of tunnels, and then a couple of slides on our future plans. So CERN is the largest particle physics laboratory in the world. There's many labs that's similar: Chicago, Hamburg, and Daisy, Japan, but CERN is the biggest one. And the goal of CERN is to understand the most fundamental laws of particles and the universe. It's nothing to do with making nuclear bombs, nothing to do with electricity, just pure research. You can see the tunnel, that's the Large Hadron Collider, 27 kilometers, straddling the French, Swiss border, Geneva Airport, and the bottom in Lake Geneva. So CERN is underpinned by 4 major missions. Obviously, the main one is research, physics research. But the other big part of CERN is education and training. We take a lot of young engineers for 2 or 3 years, and they go back into industry. Technology and innovation, not just research. There's many spin-offs from CERN, like the World Wide Web. Hadron therapy for cancer treatment was developed at CERN. But the big part I'm going to talk about is collaboration. So CERN is a big organization, international. It was founded in 1954, just after the Second World War, to get physicists working on something peaceful after the war. Started with 12 member states. It's now grown to 25. Budget about 1.2 billion Swiss francs, so equivalent to a medium-sized university. 2,700 staff, 1,200 graduates, but 14,000 users all over the world looking at physics data. It's a very diverse organization, 110 nationalities. And Portugal is a very big part of CERN. Been a member for 40 years, 123 users, 65 staff, and you can see the numbers there for the other attributes. And in fact, we just celebrated 40 years of CERN in January. Portuguese Minister of Education, Science and Innovation visited CERN. We met our new Director General, who happens to be British this time. You can see this laboratory in Portugal is a big part of CERN, not just in the Large Hadron Collider, but also many other experiments at CERN. Very successful engineer and teacher training program, and a very well-balanced return. What we mean by that is CERN checks very carefully how much a country puts into CERN, to make sure they get a fair return, either in staff or industrial contracts. And we call Portugal well-balanced, getting a good return in staff and in contracts. So now I'll talk about a tunnel. So the Large Hadron Collider is a 27-kilometre ring, about 100 metres underground on average, with a superconducting magnet, so a helium machine, accelerating particles in 2 different directions, circulating close to the speed of light, and then the magnets kick the beam in and make it collide into the middle of a detector in these big underground caverns. Basically a very large camera. The physicists analyse what comes out of the collision and to look at new research. You might have heard about the Higgs boson discovery a few years ago. It was discovered in one of these detectors. That's an aerial shot. Airport's at the bottom this time. The Dura Mountain's in the background, and we have 4 detectors: CMS, Atlas, Alice, and LHCb. But it's not just the Large Hadron Collider. In total, there's more than 70 kilometres of tunnels building up to the Large Hadron Collider, with more than 80 caverns, and we employ 50 civil engineers at CERN. The geology, so one of the reasons why CERN was picked after the war for the centre is because we have good rock. The majority of the tunnels in what's called the molasse rock, which is sandstone marl type rock, which is good for excavation, relatively dry and stable. But it does have some nasty properties like swelling, creep, and squeezing, so you need quite a lot of primary and secondary lining. On top of that, we have the moraines, which are glacial deposits for the shafts we have to go through first to get down to the good rock. And then we have the limestone rock, which in some countries is a good rock for tunnelling, but where we are, it's very fractured and caustic, so it's a very bad rock, so we try and avoid it. You can see in that plot on the right-hand side, the LEP or the LHC tunnel is in red. That's at 27 kilometres. So one sector just touches the limestone, the yellow rock. And now we're planning a new machine, which I'll talk about in a second, called the Future Circular Collider, which is nearly 100 kilometres, shown in the purple colour. So again, it's nearly all in the molasse rock, going underneath Lake Geneva, going towards the Chamonix Valley, and all the way down to nearly Annecy, but staying in the molasse rock as much as possible. Our tunnels are normally inclined, like the Large Hadron Collider is inclined at 1.4%, to make sure it's in the good molasse rock as much as possible and to minimise the depth. But just one section goes into limestone where we still have lots of problems today, leakages. So I joined CERN in 1998. The LEP tunnel already existed. That was built in the 1980s, the grey tunnel, and the red was the new. I was employed for the top one, for the CMS site, so 2 new shafts, 2 new caverns, and a few bypass tunnels. Got a few photographs. So this is the CMS site in 1999. We just started work. So you can see the 2 shafts just about in the middle. But we knew that the geology was very, very bad at the site. So the whole strategy was to build the building first for the detector, so they could pre-assemble, test the detector, while we were messing around doing all the shafts through these very difficult conditions. Sustainability, even back then, was a consideration. We made sure all the spoil that came out of the underground was stockpiled permanently and landscaped. We recreated a nice Roman footpath, built water retention basins. It's very nice. The people are very happy with the finished product. So for the shaft excavation, we had to go through these glacial deposits. So we used a ground freezing technique, drilling pipes right down to the rock through the glacial deposits, about 60 or 70 metres. And we circulated salty water or brine at minus 23 degrees centigrade down these freeze pipes until the water in the ground started to freeze around each freeze pipe. Eventually, you can see the ice here formed. The contractor started excavating, and a wall of ice was stopping water coming in and also acting as a retaining wall. That was the theory. Unfortunately, a lot of water came in. We lost over 6 months on the contract with nitrogen injections, bentonite walls, but eventually it did work. And so we could excavate all the way down the bottom, do slip form concrete lining, and then turn off the ground freezing. So the shafts are, the big one's 20 metres in diameter, the small one 12, and both about 100 metres deep. That's the finished cavern with the shaft. That's a 20-meter cavern. So the Large Hadron Collider comes to where that wooden door is. That's where the beam comes out now into this big detector. If you visit CERN now, unfortunately, you can't see the civil engineering anymore. It's filled with fphysics equipment and detectors, but it was very impressive at the time to see the excavation complete. For our excavation, we use either rock breakers or road header for the smaller tunnels. Don't use any explosives because it's quite a soft rock. And we use a tunnel boring machine if the tunnel is more than 2 kilometers long, because then it's worthwhile to install a costly tunnel boring machine. Otherwise, you can go very quick with a rock breaker or road header. So that's the past finished. The present is high luminosity. We're now upgrading the whole machine. You can see the works in red have just been completed at the top. The new shaft in a tunnel about 300 meters long, connecting tunnels. The same on the other side, on the Swiss side. This is all finished now. We just have to do some drillings down to the LHC, some cores to connect this new facility to the new one. And this is going to be a big increase on luminosity for the Large Hadron Collider. So that means the collisions will be much more collisions per second. So now the tunnels are shut down for 2 or 3 years. This is a very good time if you get the opportunity to come to Geneva to visit the underground in the next couple of years. It should be a lot easier to get underground to see the tunnels and caverns. One slide on tunnel asset management. So because the tunnels are getting very old now, we're doing a lot of work with monitoring and maintaining the tunnels. We have a nice collaboration with University College Cork on machine learning. And we're doing all sorts of research and development on fiber optic monitoring, drone technology, using robotics in the tunnel, etc., to keep an eye on the tunnels to make sure they last for the future. And now this is the future. So that's the Large Hadron Collider at the top now. This is a new planned project. It's full strength feasibility study. It's not confirmed yet, but we're doing a lot of site investigation to check the feasibility and cost estimates. It's nearly 100 kilometers in circumference underneath the lake, as I said, right around the Geneva region. So the Large Hadron Collider will be used as an injector into the new machines. That's the existing facilities at the top. This is the new one with 8 surface sites, 13 shafts, and big discussions ongoing whether there's be 4 experimental areas you see in red or 2, and lots of various little tunnels for services, which I won't explain today. But our biggest job at CERN, one of the challenges, is deciding what size tunnels do we need. So the physicists come along with the project, we want a cost estimate immediately, but we have to say, hold on a second, how big the tunnels need to be, which needs a lot of integration studies for ventilation systems, for transport, for the cable trays, etc., etc. So it takes a long time to decide what's going inside the tunnels. Then we can give cost estimates. So we're doing a lot of site investigation in the areas with the most uncertainty. We're doing, for example, you see between shafts A and B underneath Lake Geneva, we're doing 4 drillings in the lake. In the bottom left, you can see the long profile. So between shaft A and B, the lake is the depression. So making sure, for example, in that location, that we're in the good molasse rock and we're not going through the glacial deposits underneath the lake. And it's similar in the other areas to really understand the geology in these critical areas. Apart from that, there's other studies going on. The FCC is the main priority for CERN, but there's also an idea of building a linear collider in the CERN region, which is a completely straight machine. The advantage of that one is you could build the first phase, which is about 10 kilometers, the pink dots. Then you can install it, start the physics while you're planning the next upgrades of the machine, ultimately up to 40 or 50 kilometers long. And there's also a plan, which is possibly the most feasible, I don't know, is to reuse the existing tunnels we have to install another electron machine called LEP3, which will mean making the tunnels bigger, again, at CMS and Atlas, and doing a lot of refurbishment works to upgrade the tunnel to make sure it lasts another 50 or 60 years. One slide on sustainability, John talked about. So it's not just the cost, of course, we're doing a full life cycle assessment for our new projects, looking at the carbon cost and embodied carbon. And a big part of our concerns are the excavated material. We have 8 million meters cubed of rock to excavate for the future site of the collider. And it's a nice rock to excavate, but it's not a very good rock for reuse. So we're looking at all sorts of ideas how we can reuse the rock rather than just dump it somewhere. And the physicists are not short of ideas. They also have many other collider projects that we're looking at, much smaller, but still a few hundred million. These projects, not the bigger ones I talked about, but there's a lot of other ones ongoing. Just one example is called the Forward Physics Facility. So it's to do a new shaft about 90 metres deep, new cavern for a dark matter research facility. And again, we're doing site investigation, or did site investigation, to look at the ground conditions for the new shaft. And also we work internationally in CERN on many other projects around the world. So for example, we're working on a linear collider project in northern Japan, just north of Sendai. And this is probably more interested in Europe, a project called the Einstein Telescope, which is really taking off quite quickly. There's a lot of EU money in this project for site investigation phases. It's nothing to do with CERN. It's a tunnel about 10 kilometers, triangular shape, very, very deep, and it has to be very, very quiet. It's a system of lasers and mirrors to measure gravitational waves from space. So it's not accelerator, just measuring what's coming from gravity. And there's 3 proposed sites at the moment. There's one in Maastricht, one in Eastern Germany, and one in Sardinia. The 3 sites are being considered for which one will be eventually selected. But there's a lot of money going into this, and more than likely will go ahead. I've talked about the underground, but I could talk forever about the surface buildings as well. We do a lot of work. We have 600 buildings on the surface. We just started a new one on our French campus now called Building 777. A very modern wooden type structure. Companies, lots of work for companies at CERN. We normally do FIDIC type contracts with full design by the consultants and the contractors to do the execution. That was for Large Hadron Collider, about 600 million. And now we're looking at the future cellular collider, which the civil engineering estimate is between 5 and 6 billion Swiss francs. We have a lot of consultants on board doing the pre-feasibility design, looking at the spoil disposal, the geotechnical aspects, geology, etc. And we placed a couple of contracts with 2 companies for the actual drillings in geophysics. But there's more coming out all the time, so any companies interested in work, there's lots more coming up. And the last slide is a plug for people. CERN's not just about contracts, also about people. We employ 10 times more engineers and technicians than we do physicists. So there's many, many jobs for civil engineers, mechanical, electrical engineers, lawyers, accountants, firefighters, etc. So if anybody knows any particularly young people who like for a job at CERN, there's a website there. I can get in contact with us. Yes.
60 seconds and we can all go network downstairs. Thank you all for being here. Thank you to all the speakers. Amazing presentations. We're only 15 minutes late, and I think that is great, considering the amount that we've covered. I think that's excellent. There are really only 3 thank yous to say, which this event wouldn't happen. So I think first from the Ordem, Beatriz Martins, who couldn't be here, but Beatriz Encarnação.
The other way.
The other way, sorry. Oh yeah, it is. Beatriz Encarnação couldn't be here. Beatriz Martins is here. I'm very tired. And finally, Tom Compton, who's sitting over there and who coordinates the logistics of getting 18 people to Porto on the right metro, out of the right in the right hotel, and walking over all the bridges. But thank you very much, and we'll see you downstairs. Weinbeich?
Yes, downstairs next to the secretary.
Okay, perfect. So we see you all downstairs.
Wait, usually my worst. So